Okay, so now we want to talk about water specifically and some of its unique properties. As you recall, water is a polar molecule, and it's that polarity that in part is responsible for many of these interesting properties. First of all, high heat capacity or heat of vaporization. What that means is that it takes a lot of energy to change the temperature of water. All those hydrogen bonds that are in water have the ability to absorb a lot of energy. And more specifically, as something you'll get hammered home in chemistry, it takes basically 1 calorie of energy to change 1 gram of water 1 degree Celsius. And so compared to other substances, that's a relatively large amount. Metals like iron and tin and bronze have much lower heat capacities. So when you cook something on the stove and you heat up a pan of water, the pan heats up a lot faster than the water itself. You would not want to touch the pan, a minute or so after turning on the heat, but the water would still not, it might be a little warm, but not that warm that you couldn't touch it. So what does this mean for living things? It means that since living things mostly consist of water, their temperature doesn't change very much. You walk outside on a hot day and your body just doesn't all of a sudden heat up, or you walk outside on a cold day and your body doesn't rapidly cool down, because all that water inside you, it takes a lot of energy to change its temperature, so it changes very slowly. And of course, with your metabolism, you try to keep it at the same temperature. You don't want it to change, and all that water allows that to happen. All right. Of course, in any kind of solution, you have the solvent and solute. The solvent is the liquid. The solute is what's dissolved in the liquid. And for our purposes in living things, water is the universal solvent. Universal. What would universal suggest? That anything will dissolve in it? Well, it's not quite universal, because not everything will dissolve in water, but a lot of things will. You put sugars or salts in water and they readily dissolve. So water is a good solvent. That's important for us. Our blood, our body fluids, again, are water-based, and so the water is able to carry lots of different materials dissolved in that solution. And specifically, a solution in which water is the solvent is known as an aqueous solution. So remember that. And for living things, it's all about aqueous solutions. Again, those water molecules are sticking to each other. So what that means is that water molecules stick to each other. That's cohesion. And they will stick to other things, other materials that have a charge, and that's adhesion. So water generally sticks to glass because glass has a charge. In trees, in the small vessels that go up trees that the water travels up, it sticks to the sides of the vessel a little bit, and that helps hold the water up in the tree, keeps it from falling down with the force of gravity. And as you've probably experienced in middle school science, capillarity, when you take a small glass tube and stick it in water, the water travels up the tube a little ways because, again, the water molecules are sticking to each other and they're sticking to the sides of the glass tube. Now, why don't they go all the way to the top? Well, that's because of gravity. They can only go so far. All right, so the sticky nature of water as well creates what's called surface tension, or we might say that the water has sort of a skin on it that something very light does not break the skin. It just kind of bends it, depresses it a little bit, like this water strider here. You can see that its feet are basically depressing the water a little bit, but they're not breaking the surface tension, and so that's why this guy is able to basically walk on water. Now, larger or heavier objects doesn't work because they break the surface tension. All right, another unique property. When most things become colder, they become more dense. That is, the atoms in that material they move slower and slower, and they become more tightly packed together, and that thing becomes heavier. In other words, per unit volume, there's more of the molecules. It's now heavier than when it was warmer. Now, this happens to liquid water. You can see that as it's getting colder and colder, it's becoming more dense, but it basically reaches its maximum density at about 4 degrees Celsius. And then after that, it starts to become less and less dense until finally it freezes and it becomes really low density, less than the liquid form. And that's why ice freezes. Essentially, the water molecules are now further apart from each other than they were when they were in the liquid phase. There's lots of hydrogen bonds forming, basically locking those water molecules in place. So that's a unique property. It's why, of course, ice floats, and on lakes, why they freeze from at the top and not the bottom. Okay, because water is a good solvent, what that means is that things will dissolve in them or they will readily ionize in them. So when you put a salt, sodium chloride, in water, as you know, sodium chloride is an ionic compound. What happens, it'll start to break apart as those charged ions, the positive sodiums, the negative chlorine atoms, start to stick to the water molecules. So that's why things with a charge will dissolve in water, because they start sticking to the water molecules. Now, the water molecules itself will also ionize, and that is, in any aqueous solution, some of the water molecules break down into the positive hydrogen ion and the negative hydroxyl ion. Now, the hydrogen ion, or what is essentially a proton, because that's what most of the mass of a hydrogen ion is, it consists of a proton, will then sometimes bond with a water molecule to form what's called hydronium. So you essentially have these two ions, the negative hydroxyl and the positive hydronium, in the water with all those water molecules. Most of the molecules are H2O, but some are OH negative and some are H3O positive. When the amount of these are equal to each other, you basically have what you call a neutral solution. But we'll see that when the amount of hydronium is greater, you have an acidic solution, and when the amount of hydroxyl is greater, you have a basic solution. So that leads us into the notion of pH, which officially pH is really a measure of the amount of hydrogen ion, or basically hydronium, in a solution. Okay? And there are certain compounds that when added to an aqueous solution will make it more acidic or more basic. And of course, to make something more acidic, you have to add an acid. And some good examples: HCl, or hydrochloric acid, chloric, and sulfuric acid, chloric acid, HNO3, nitric acid. Notice that all of these have this H's out to the side here, that when this is put in solution will tend to break off, so that when you put hydrochloric acid in solution, the hydrogen ion breaks off, and the chlorine atom breaks off. So now you're increasing the amount of hydrogen ion, which means you'll increase the amount of hydronium, which means this solution will become more acidic. The chlorine ion in this case makes no contribution to pH. It's just the negative hydroxyl and the positive hydrogen that influence the pH. Bases will be compounds such as sodium hydroxide, lithium hydroxide, and calcium hydroxide, who have these hydroxyl groups that will tend to break off, thus forming the sodium ion and the hydroxyl ion. And so now that we've increased the amount of that, this solution becomes more basic. So acids and bases. Acids will give off a hydrogen, bases will give off a hydroxyl group when they're in solution. So let's say we have a solution that starts out with this concentration of hydronium. It's pretty low concentration, but there's still some there. 1, 2, 3, 4, 5, 6, 1. That's supposed to be a 1. Alright, and we're going to add enough acid to get the hydronium ion concentration to this level. Alright, if you do the math and you take 0.0001 divided by 0.0000001, basically equals 1,000. What does that mean? Well, our solution now has a lot more hydronium ion at the end than when it started, and it's now basically 1,000 times more acidic. Alright, so let's take a look here. That solution we started with, 1, 2, 3, 4, 5, 6, had 6 zeros. It was basically a neutral solution. That is one where the hydroxyl ion is equal to the hydronium ion. A neutral solution. We added acid to it, such that now the hydronium ion concentration increased, and it increased basically down to a pH of 4. And remember, that we calculated was 1,000 times more acidic. So let's look at our pH scale here. It goes from 0 to 14, with 7 being neutral, things less than 7 being acidic, solutions greater than 7 being basic. We've gone from 7 to 4, and it's 1,000 times more acidic. So let's look here. If we were to just go to 6, that would be 10 times more acidic. If we went to 5 compared to 7, it would be 100 times more acidic. And then to 4, 1,000. So basically each time you move a unit in the pH scale, it's becoming 10 times more acidic or 10 times more basic. So 10 times 10 times 10 gives us our 1,000 times more acidic. So the scale is not, it's not what we would call a linear scale, but it's a logarithmic scale to the base 10. It increases by a factor of 10 each time you go through the scale. And you could do this calculation as well. You can see we're going from that same hydronium ion concentration, or a pH of 7, and now we're going to, goodness, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going really basic, which I think 1, 2, 3, 4, 5, 6, 7, 8, 9 is right here. 11, pH of 11. Oops, not a pH, but a pH of 11. So now we're going 1, 2, 3, 4. What's that? 10 times 10 times 10 times 10. So this one, we've now increased, or the acidity has decreased by a factor of 10,000, or it's 10,000 times more basic. That is, there's less of the hydronium ion, or you could say more of the hydroxyl ion. All right, last thing, the scale again from 0 to 14. You can see these are just some various compounds and where they fall on that scale. Pure water is neutral. Ooh, tears, approximately neutral. Your blood is just slightly basic. Sodas, drinks, stuff like that, they're quite acidic. Of course, lemon juice, you're not surprised there, is very acidic. Look at your stomach acid, really acidic. There's lots of hydrochloric acid secreted in your stomach that helps digest that food. And baking soda, ammonia, these things are some soda. Of course, there's sodium hydroxide, that one of those bases on the far end. Okay, so there's the wonderful world of water.